Good. So yes, what we've seen that these formulas, ABPs, circuits, and we've seen ABPs. Okay. With that, I didn't show you this. I mean, I won't. You can find it in the surveys maybe, and if not in the surveys, you can find it. Okay, I need to correct something I said earlier. I was asked about separations between VP and VQP. And I said in the multilinear world it's known, so I meant something else. But someone said that Shpilka said it. Don't listen to what I say, listen to what I mean. So what I meant is the following. So let's define also the classes of V and C. Let's say V and C1 and V and C2. So these are circuits of depth O of log n. So you have n variables, and the depth of the circuit is logarithmic, and fanning 2. So when we speak about NC, we allow only fanning 2, okay? And these are going to be depth log square n, okay? So Ram Prasad is going to speak after me, right, in the tutorial, and he's going to speak about depth reductions. And then what we are going to show is that you're going to show that VP is contained in V and C squared. And if we restrict ourselves to poly size, then it's actually the same. Okay, so if you, I mean, the definition should be V and C squared, it's circuits of polynomial size and depth log square. Then this is a theorem. Prasad is going to speak about it. I don't think we'll show you the proof. We'll show a lot, I mean, many things, but not the proof. But it basically says that polynomial size circuits, arithmetic circuits, can be parallelized, could be made parallel, right? So depth only log square. In the Boolean world, we don't know it. And when we spoke about separations, in the multilinear world, we have an example of polynomial that sits in VP. So it's determinant, and it does not have V and C1 circuits. So V and C, it's basically, it corresponds to formulas. Every circuit, polynomial size circuit of depth log n, also has a polynomial size formula, because basically you can just open the tree, right? I mean, even if you have edges, since the fanning is 2 and the depth is logarithmic, you can just copy things when you need to use them again. So you can open a tree, you can make a circuit into a formula, and the size of the formula, if the fanning is 2, it's going to be 2 to the depth. So when the depth is logarithmic, it's going to be polynomial size. And also formulas, polynomial size formulas could be balanced, so they could be made to have depth log n or O of log n. So basically this is the class of formulas, and this is the class of circuits. And in the multilinear world, we have separations between those two. Now if you would like to open this to a formula, you'll get a quasi-poly formula. So we do have an example for a polynomial that has a quasi-polynomial size multilinear formula, but does not have, sorry, it's not multilinear again. We do have an example of a polynomial that has a quasi-polynomial size formula, but not a polynomial size multilinear formula. Okay. So that's the separation that we have between VQP and VP. So it's okay. It's not VQP and VP, it's something else. Okay, so this is about depth reductions, but already let me use this thing. So what does this say? This says that everything that has a polynomial size circuit also has a circuit of depth log square. Now by what I told you, if you have a circuit of depth d, you also have a formula of size 2 to the d, right, if the fanning is 2. And this reduction makes fanning 2. I mean, it's going to have a constant fanning. So this is contained in quasi-poly formulas. Okay, because 2 to the depth is quasi-poly, and this is contained in quasi-poly determinant, right? I mean, okay, take it with right. So quasi-poly size ABP is a projection of a quasi-poly size determinant. So basically, everything that is in VP can be represented as a determinant of a quasi-polynomial size matrix. And actually, if you think of quasi-polynomial, then it equals, okay, depends on the quasi, but basically V and C of 1. Depends on the quasi-polynomial that you have here. And then this sits into again, quasi-positive formula, and that's okay. So this Ramprasad will show those kinds of reductions, or at least we'll speak about them. But this shows that the determinant is complete for V cube. You can compute it in, I mean, as a determinant as a small circuit, so it's in VNC square, so it says a quasi-polysize formula, say, if you want. Okay? So these are the reductions, and this is the completeness of the determinant. That's what we mean by saying that the determinant is VQP complete. Okay.
The proof relies on depth reduction, so this is something you haven't seen yet?
Yeah, you haven't seen the depth reduction. You need to, I mean, the starting point is that every polynomial size circuit can be computed by a quasi-polysize form. That's the starting point, and then continues. Okay. Great, so I think this covers what I wanted to say about complexity classes and about complete problems. So we've seen VP, VNP, quasi-polynomial, and the NC classes. We said that permanent is VNP complete. We haven't shown that. We said that the determinant is VQP complete. This we've seen. We haven't seen the circuit for the determinant, but it's there. And now what I want to do is I want to switch topics. So that was like the big picture overview of the field. I'm presenting the big open problem of VP versus VNP. Now what I want to do next is I want to start saying, okay, what can we do with arithmetic circuits and give some structural results about it. So one structural result, for example, is this, but that Ramprasad will show. What I'm going to show is I'm going to give you now like a toolkit, things you can do with arithmetic circuits quite efficiently. So this toolkit will speak about what interpolation, homogenization, taking partial derivatives. And I would also like to say about why we don't need divisions. Okay, so that's what I want to do next. Okay, so it's a completely, so up till now things were more about complexity things and reductions. Now we're going to be more specific and speak about building circuits for certain tasks. Okay. Okay, so what is the interpolation question? So usually we speak about interpolation in one variable, right? Let's say that we have f of x is univariate. So we can write f as summation alpha I xi, or maybe call it ci, the coefficient, to 0 some degree d. So we have a univariate polynomial, and we want to, as I said, I'm giving you d plus 1 values of f, so all alpha I are distinct. And I want to move from those values to the coefficients and vice versa. I mean, if you give me the list of coefficients, I want to be able to compute that. And if you give me the list of values, I want to compute the coefficients. So there are two, okay, I mean, maybe you've seen it as an exercise in linear algebra 1, maybe you haven't. So let me solve that exercise for you now. So, I mean, there are two, simple and equivalent ways of doing it. One using the Lagrange polynomials, and one using the van der Monde matrix. I'll do the matrix because I think it's slightly more elegant. So what happens here? So what does it mean to evaluate the polynomial at a point? It means that you take the vector of coefficients and compute an inner product with the moment curve, right? So basically you can look at this matrix, 1, alpha 0, d, 1, alpha d. And you see 0, c, d. Now what does this give you? When you take this product, it basically gives you f of alpha 0 to f of alpha d. Right? That's what you get. Simply, you evaluating at the point, it's just taking the inner product of the coefficient vector with the moment curve of the appropriate degree. And so it's clear how to move from one representation to the other. If I tell you those points, and I give you the vector of coefficients, well, you just multiply. If I give you those values, you just multiply by the inverse of that matrix. That's it. Right, so that's interpolation. Right, that's one way of seeing it. Another way is writing it, I don't know if it's more explicit or less explicit, it's up to you. I mean, the way I think, but we can also write another way of seeing it, it's using the Lagrange polynomials. We can define the ith polynomial of x to be what? It's going to be a polynomial that gets 1 at alpha I and 0 at all the other guys. So it's going to be product of j different than I, x minus alpha j. So this guy, when you plug in any of the alpha j's, it's 0 unless you plug in alpha I, and then you get something which is non-zero. So just to normalize it, we'll just do this. So this is Li of x, and Li of alpha j is just 1 if I equals j, and if j is 0. And then you can see that f of x is just summation. If I go from 0 to d. So if you think about these two polynomials, so by the way, what is the degree of this polynomial? So we have d plus 1 values, but we multiply only d of them. So this is a degree d polynomial. So this side is a degree d polynomial, and that side is a degree d polynomial. And if you think about it, whenever you plug alpha I, what do you get? Here you get f of alpha I. And here all the summands are 0 except the Li of alpha I, which is 1 times f alpha I. So these two polynomials agree on d plus 1 points. And so if you subtract one from another, you get a degree d polynomial that has d plus 1 zeros. And it must be a 0 polynomial. So the two representations are the same. Okay, so that's interpolation. And the reason that I mean, what's the connection to arithmetic circuits? It basically tells you that if you have an arithmetic circuit and you have some variable, and you know that that variable appears at degree d, then by evaluating the circuit at d plus 1 points, you can get access to the coefficient of that variable. So let me write it again. So with a corollary. So if f of, let's say, x1 up to xn, let's say a variable y, as, okay, if f, let's write it like this. It's summation, I go from 0 to d, it's y to the I times some coefficient, but that coefficient is some polynomial in x. Right? Every multivariate polynomial, I can look at the coefficient of y to the I, it's going to be some polynomial in the x variables, and I expand it like that. And now, if what I want to say, everything that you said so far means that if f is a small, I want to say that now if f is a small circuit, then each of those CIs also is a small circuit. So, if f then, and f as a size S arithmetic circuit, then each CIX is a size, I guess, O of S times D arithmetic circuit. And what is the reason? The reason is what we said, right? I mean, to get the coefficient, you just need to take evaluation at d plus 1 points. So it means that you take the circuit for F, and first you plug alpha 0 to Y. That's one copy of the circuit. Then you plug alpha 1 to Y. That's another copy of the circuit. Up to alpha D, so you have d plus 1 copies of the circuit. Right, think about it as just as a polynomial in Y. Forget about the x's, right? So you plug in alpha 0, it's give you one value, alpha 1 gives another value, alpha D gives another value. And then, by what you see, you just need to take a linear combination of that values, right, according to the inverse of that matrix, to get the CI. So you just take all those circuits and then connect them with some linear, with some appropriate coefficients. And that's give you a circuit for each CI. Okay? So, yeah. Right, so we need so we need n plus 1 elements. So we need a field. Okay, excellent question. I should have mentioned it. So when I presented the circuit for the symmetric polynomial, I basically did interpolation, right? You remember I looked at the polynomial pi of y plus xi, and then I computed the coefficient. So I did interpolation. And then I said that it doesn't work over GF2. Now, why doesn't it work over GF2? Because I cannot do interpolation there. Why I cannot do interpolation over GF2? Because I have only 2 field elements and not d plus 1 or n plus 1 field elements. So I can do this for every field in which I have at least d plus 1 elements. Right? Whenever can I do it? This is the important thing. The alpha i's are distinct. If you give me distinct elements of a field, then since they're distinct, this is not 0. So the product is not 0, so it's invertible. So all the thing works as long as you have d plus 1 distinct elements. And if your field does not have d plus 1 distinct elements, you can either say give up or go to an extension field that is large enough and has d plus 1 elements. But for interpolation, yeah, we need the field to be at least the size of the degree. I mean, maybe there are other ways of computing the coefficients, but as I defined it, but this process needs at least d plus 1 elements.
My question is actually slightly different.
Ah.
So in the univariate interpolation, you only divide by field elements. But now when you want to do this interpolation,
it is a matrix of constants.
No, these are field elements, so the inverse matrix is also with field elements. Right, just the inverse of the matrix. It's everything over field, yes.
the F's are polynomials, but they are not...
The F, yeah, I don't care. The F is something. I mean, it only depends on the alpha i's, right? The variation. I mean, what the coefficients are here. Okay. Good. So that's interpolation. So if we have a circuit and I say, look, for certain task, I need that coefficient. So you know that the price that I pay is relatively minor, right? To extract the coefficient is minor. But just notice that it's a coefficient in one variable. So earlier we said that, remember the example with the permanent? We took a polynomial. So getting a coefficient that involves n variables can be, we have to repeat this iteratively and then the size blows to exponential. So extracting coefficient in one variable, I mean, the cost is relatively low, but if you want to take a coefficient of a monomial involving many variables, then you have to pay a lot. Okay, good. So that's interpolation, and now let's talk about homogenization. So, definition, what is a homogeneous polynomial? Fx is homogeneous if all monomials have the same degree. Okay, that's the definition. So degree of a monomial I didn't define actually, maybe I should have, but right, so the degree of x1 to the e1 up to xn to the en is just the summation of the ei's. Right? It's the total degree, the sum of degrees of all the variables. Right, that's the degree of so for example, so as an example, so I don't know, sigma and d, determinant, permanent, are all homogeneous, right? In the permanent, all monomials of degree n, determinant, same thing. The symmetric polynomial of degree d is just the sum of monomials of degree d, but are all homogeneous. But for example, x1, x2 minus x3 is not. It's not homogeneous. That one is degree 1, this one is degree 2. Similarly, x minus 5 is not homogeneous. Degree 1, degree 0, okay? So that's homogeneous setting. That's an homogeneous polynomial. And a circuit is homogeneous if all nodes compute homogeneous polynomials. Right? So an input clearly computes a homogeneous polynomial because it's either a variable or a constant. Each of them is homogeneous because there's only one monomial. But as you go along, you compute more and more complicated polynomials. And we say that the circuit is homogeneous if all the intermediate computations and the output are homogeneous. Okay? And here is some theorem, which is, it's very useful and it's pretty simple to prove that if f is homogeneous of degree D, and as size S circuits, then F as a size O of SD square homogeneous circuit. Okay, so if you want to compute homogeneous polynomials and you don't care about polynomial blow-ups, then you can also assume that the polynomial is computed by a homogeneous circuit. Or alternatively, you can also say that if F is degree D and size S circuit, then, okay, maybe I should have defined it, then, okay, you know what, I think I don't have enough space, I'll just move here. Okay. So maybe before I continue the theorem, let's say that maybe we'll call Fi the homogeneous component of F of degree I, which is the sum of all monomials or terms, right? I mean, we take also the coefficients of degree I in F. The sum with coefficients of all monomials of degree I in F. Okay, so you have a polynomial. For example, here the degree 2 part will be x1, x2. The degree 1 part will be minus x3. In sigma nd, the degree d part will be the entire polynomial. The degree d minus 1 part will be 0. The degree d minus 2 part will be 0, etc. Because you don't have monomials of degree other than d. Okay, so you just take all monomials of a given degree. And then the theorem says that if F is degree D and size S circuit, then there exists a homogeneous circuit for F0, F1 to Fd. So it will be a circuit with many outputs, and it will be homogeneous. Okay? Okay, so let's see the proof. Good, so what do we have? We start from a polynomial. I'll just prove the statement about homogeneous polynomials, and the proof for this is the same. Circuit of size SD squared. Maybe I need another factor of D. No, we don't. SD squared. Okay? It is actually, it's the same circuit. Yeah, okay. So, no, it's the same. It's one circuit with many outputs. You're going to have D plus 1 output gates and one circuit. Each node in the circuit computes a homogeneous polynomial, and there are going to be D plus 1 designated outputs that compute those polynomials. Okay, so what do we do? So basically, what we do is actually pretty simple. For each node, we are going to keep, each node in the circuit computes a polynomial. So we're going to split each node to D plus 1 nodes. One of them will carry the homogeneous part of degree 0 of that node. One of them will carry the degree 1 homogeneous part of that node, etc. Okay, so start with the circuit for F. Split each node V to say V0 up to V D. Okay? So I take a node and I not split, maybe replace each node V with. And now I have to tell you how to rewire. If if U and W are children of V, I have to tell you how to rewire things. And I should have also said, listen to what, let's assume that fanning 2, okay? To a circuit for F. Right, moving from arbitrary fanning to fanning 2, increases the size by a factor of 2, so it's not a big deal, right? Because whenever we have a large fanning, you can build a small tree, right? So let's assume fanning 2. Okay, so we replace each node V with D plus 1 nodes. And now I have to tell you how to rewire those nodes. So if V, so V can be either two things, right? It can be either a sum of two children or a product of two children. So if V is U plus W, then what do we do? So what is Vi then? What is the degree I part of V? It's a sum, right, of the, then we do this. So for each I, we put those two edges. So we originally we had two edges, right? We have a plus, and now we have D plus 1 times 2. Okay? What happens if V is U times W? So what is the, let's say, right, what is V, okay, let's say K, Now what is the degree K part of V? How do you get it? How do you get the degree K part? Either you take a degree 0 from here and degree K from here, or degree 1 from here, degree K minus 1 from here, etc. Right? So it's summation, I go from 0 to K of U I times W K minus I. Okay? So for each K, how many edges did we add? So a product is two edges, and we have a sum of K things. K is at most D, so it's like O of D many edges. And we have D guys. So whenever we do this splitting, if we had a plus gate, we add O of D edges. If we had a product gate, we add O of D square edges. So overall, we had, if we started with S edges, we end up with S times D square edges at most, or O of S times D squared. Now, what happens at the output gate? The output gate, and you can then claim the polynomial computed at Vi or Vk is the kth homogeneous component of the polynomial that originally computed at V. Okay, so that's the main claim. And the proof is by induction, yes.
You basically just need to compute the convolution of these.
Yes.
If you try to do it more efficiently, it's no longer homogeneous? Or
No, it's going to be homogeneous. It's a bilinear circuit. No, because you mix, right? You take sums and stuff, right? You're right. Yes. Okay, so you can prove the claim yourself. It's trivial. Everything's basically on the board. So that's it. So now if you look at the output gate, so you also split the output to D plus 1 values, and the ith value of the output will compute Fi. So that's it. So in many cases, especially in depth reduction, and also in other settings, it's very convenient to work with homogeneous polynomials. Because, all the degrees are the same, and you know what happens to the degree when you multiply it. Terms behave nicely. And what this theorem shows is that you don't lose much by assuming the circuit is homogeneous. Okay. So that was how to move from homogeneous polynomial to homogeneous circuit, or basically from any circuit to an homogeneous circuit. And yeah, so this is fanning 2, and then you have the sum of K stuff.
The top V is equal to U times C. Is that V is equal to U1 times U2 times U3?
Yeah, then you take a large convolution, which is more complicated. So I prefer to go to fanning 2 and then do that. Right. If we didn't have fanning 2, then we will have a more complicated convolution. So that's much nicer. Yes.
Just to say that this also
resulting circuit, none of the intermediate computations compute polynomials of degree more than what your output is.
Right, right, okay, yes, thanks, Ramprasad. Yeah, I mean, originally when we defined arithmetic circuits, we didn't bound the degree of the circuit, right? I mean, even if you want to compute a polynomial of polynomial degree, in principle, from the definition, the circuit could go to huge degrees and then use cancellations and give you the output. And what this shows you is that it doesn't, that without loss of generality, the circuit, you don't need to take degrees of larger than what you compute, right? Except, sorry? So if you speak about arbitrary circuits, arbitrary arithmetic circuits, then without loss of generality, you can assume they are homogeneous, and therefore you never go above the degree of the output polynomial, right? Because we only have V0 up to Vd, so we don't have more than D. However, if you start making further restrictions on the circuit, like reducing its depth by a lot or something, then you cannot always homogenize. Because if you see, as you see, I mean, this homogenization process introduces, right, if earlier you had only one layer, right, a product gate, now each product gate is replaced by sum of products, right? So if you want to consider things like depth-free circuits, then this homogenization process introduces more layers. And then you no longer have a depth-free circuit or a depth-4 circuit. So homogenization is possible when you speak about general circuits, but in small depth, it can have a huge cost to homogenize things, and Ramprasad will actually show it, or Ramprasad or I actually will show it tomorrow, that you cannot homogenize small depth circuits. I mean, and maintain low depth. Okay, and perhaps just another comment to connect this to interpolation. So let's say that we have f of x1 up to xn. And this is, of course, f of 0 plus f of t. Okay? Let's do the following simple substitution and consider the polynomial z times x1 to z times xn. Okay? So we multiply every variable by a new variable z. Then what happens? When you have a degree, a monomial of degree k in the x variables, it will now, what will happen to z? Whenever you have x1 to the e1, you will also get z to the e1. You have x to the e2, you also get z to the e2. So basically, this will give you a summation of z to the k, f. Okay. Right? So if you just need to access the kth homogeneous component of f, you can do interpolation on the z variable, right? And then get a circuit of size s times d, rather than s times d squared. Okay? So using interpolation, right? Because you have to evaluate the d plus 1 point and then take linear combination. And it also maintains formula, right? I mean, if f is a small formula, you get a formula. So, and this process is very not formula-like, right? Because you need to somehow, the same wk will have to go to many things. And actually, there's also a homogenization process for formulas that maintains polynomial size, but only for polynomials of very low degree. So I will not cite it, but we can homogenize formulas as long as they compute polynomials of small degree.
Why do you need the interpolation? Doesn't the construction gives you the homogenization?
Yeah, but I mean, I save a factor of d, and a formula remains a formula. Here, you get a circuit. And if this was a small depth, interpolation, what interpolation does, it just adds another level of additions at the top. Right? I mean, how does interpolation look like? So, okay, so let's say corollary, right? So corollary, that if f is a small formula, then so does f Okay? But this formula is not going to be homogeneous. It's just going to be a formula, right? It's a formula that computes the homogeneous part. It's not going to be a homogeneous formula. And similarly, if f is okay, depth D formula, or D is not good, depth capital D formula with a plus gate at the top is a small, then so does fk. Right? Because in interpolation you do what? You take the formula, you substitute values, so you take d plus 1 copies of the formula, you substitute values, and then you have to take some summation. And since you have a sum of sums, then you can crush it to a single sum gate. So that's something that it's good to remember.
The size, when you count, to do the interpolation, you have to multiply by a matrix. But why is it just?
No, it's not a multiply. You just take a linear combination.
I only want one coefficient.
Yes. And if you want all of them, then you pay another factor of d. Okay, so I guess that now I'll need to show how to get rid of divisions. And what time? I have 12:30 or? Okay, I think I'll steal a few minutes because there's always some friction between going out and going in. So yeah, I just want to finish with divisions, and I guess that partial derivatives will be covered by Ramprasad. Okay, so what I want to do next is I want to explain why we don't need divisions. Okay? So, good. So I want to use this trick, so maybe I'll. So getting rid of divisions, or GRD. Okay, so we want to get rid of divisions. Okay. So I want to, I guess, okay. So now think about a circuit with plus, times, and divisions. Okay. And that computes a polynomial at the end. Okay, you use divisions like in Gaussian elimination, but at the end you get a polynomial. And I want to show that you can get the same polynomial without divisions. So here's what to do. Okay. So let's assume for simplicity, okay, so assume that f that we compute is homogeneous. It would just be to simplify things. Okay, what we said, it's not a big deal because you can compute each homogeneous component if you have a small circuit, etc. So let's assume it's homogeneous. Now, each gate in the circuit now does not compute a polynomial necessarily, but some rational function, right? Because you have divisions. So what we are going to do, we are going to split each gate to the numerator and denominator. I'm just going to keep trace of both. Okay, so split. So again, so replace.
To assume that the circuit is, you assume that
the function is homogeneous, not the circuit, just the output. Yes. So replace each v with v numerator and v denominator. I don't know. Okay. So intuitively, the polynomial computed at v equals f v numerator divided by f v. By f subscript v, I mean the polynomial that is being computed at the vertex v. Okay. So I want to keep this thing. So again, like what I did earlier, I mean, we start from the inputs. At the input, it's clear, right? You only have the denominator. The denominator is 1. What happens at now, if v is u times w, then the numerator multiply, and the denominators multiply. Right. what happens if V is U divided by W? Then the numerator is UN times W denominator, yeah, and UD times WN, right? That's a lemma, okay? And what happens at the multiplication gate? At an addition gate, if V is U plus W, well, you know what you do, right? V numerator is UN WD plus UD WN. Denominator is UD times WD. Okay? So basically, these simple equations tell you how to rewire the circuit. So now, just notice, we don't have divisions. But for each gate, we know the numerator and denominator, right? And we have it throughout the circuit. So what do we get? So we get a circuit, and it has two outputs, right? The numerator and the denominator. So that what? So that F is, right? So if ON OD is the output, then right, then F is okay. Maybe it's I'm using notation. Okay, I'm writing ON divided by OD rather than the polynomial computed ON, etc. So that's what I need to compute. Okay.
I missed the notation. So both are V.
It's the numerator of V and denominator of V. And if V is U times D, W, you need to compute the numerator from the numerators.
Right. So what is N? Vn.
The numerator, yeah. Okay. So at the end, I need to compute this. So what do we? What is the situation? We have a polynomial size circuit that computes two polynomials, and I have to take their division, and I know that the result of the division is a homogeneous polynomial of degree D. Right? I have that knowledge. Okay. So let's assume, okay, so I'm going to write without loss of generality. If you think that I'm restricting generality, then think about it more. And assume that the denominator is of the form 1 minus h, okay, where each monomial in h has degree larger than at least 1. Okay, so that basically the constant coefficient is 1, and that's it. Okay? And why it's without loss of generality? I don't want to write it, but just think about it, because if you shift the variable, because if it's not the case, then shift the variable by a constant, and you'll get that. So things will not be homogeneous now, but still assume things are homogeneous, because again, it doesn't matter. Okay, so I'm waving my hands, but really, I mean, whatever I say can be formalized correctly. So just to simplify the exposition, let's make this assumption. So we have to compute ON over OD, and this is the situation. Okay?
But doesn't that mean just multiply the two polynomials by a constant?
Not necessarily. I mean, this is not necessarily homogeneous.
But what is your assumption?
That OD is 1 minus h. No, because maybe, I mean, the only question is whether it has a free coefficient or not. What do you do if it doesn't have a free coefficient? That's the only thing. So it doesn't really matter. I mean, it's like, but I mean, I don't want to get it. It's a delicate, I mean, it's okay. So basically, if you think about a power series, right? So what you get is that F is, okay, so what is 1 over 1 minus h? We know that as a power series, this equals h plus h squared plus, etc., right? 1 plus, thanks. Right? As a power series. Okay, maybe. Right? That 1 over 1 minus h is this. So basically, ON over OD is ON times 1 plus h squared plus HD plus stuff. Right? So we know that, so F equals this, and it equals that. Now this is an infinite sum, right? However, F is homogeneous of degree D. So we need the degree D homogeneous part of that guy. And what do we know? We know that if you take, remember, in H, all monomials have degree at least 1, right? Because it has no free coefficients. So the thing that come here, h to the power d plus 1, h to the power d plus 2, etc., all monomials there are of degree d plus 1 and more. So they have zero effect on the degree d part of the product. So basically what I claim is that f also equals, if you take O(n) times 1 plus hd, and for this you compute the d homogeneous part, right? Because f is homogeneous, so you only need the degree d homogeneous part. You can throw away all monomials of degree larger than d. So, and that's great, right? Because we have a small polynomial for h, right? Because if O of d is this, then certainly h is a small circuit because you just take 1 minus O of d. So each power of h is a small circuit. So this guy is a small circuit, this product is a small circuit, and computing homogeneous component can be done efficiently. So in polynomial, so with a polynomial blow-up, you can compute the same polynomial but with no divisions. Okay? So that's basically why we can assume without loss of generality is that we don't use divisions. And again, if you start from bounded depth stuff, etc., this can be costly, but let's not worry about it. It's not very costly actually, but let's not worry about it. Yes?
About this power series 1 over 1 minus h. So we are talking about symbolic formal polynomials. So assuming h is x, it's not precise. Y is 1, it's a rational function, 1 over 1 minus x.
Yeah, I mean,
it's equal to 1 plus x.
it's okay. So, right. So in power series terms, this is an equality. If you think about Taylor expansion, then around it's inequality, but you know that this is a polynomial. You know that this over this is a polynomial. So you know that as a power series, if you take O and multiply it by this, and you do all the cancellations, then you'll get a polynomial. So I can cut it at the point where I know that things from that point onward are going to cancel, and then take what I need from what I have. Okay, so yeah, I wanted also to speak about partial derivatives. So maybe I'll just say it and wave my hand, and you'll have to live with it. So what is a partial derivative of a polynomial? Just, taking a derivative according to a variable. And if you think about it, to compute a partial derivative, you only need to know the coefficients with respect to the polynomial, right? What is the partial derivative of a polynomial? Right? Yeah, as time shrinks, also the board shrinks. It's what Einstein said, right? So if you have summation of ci x to the I, now what is the derivative with respect to x? The derivative will be summation of I times ci x to the I minus 1, right? So if you can compute efficiently all the coefficients, then you can multiply each coefficient by I and then by x to the I minus 1 and get access to the derivative polynomial. And why can we compute all coefficients? Because you can do interpolation. So even if the coefficient is a polynomial in other variables, you can compute efficiently the derivative with respect to any variable. Okay, that's what I want to say about derivatives. Okay, let's take a break.